voltage. The electric potential field is a topographical parameter. The source charge sets up an electrical landscape that tells the electron how to move. Furthermore, using potential fields immediately connects one to energy interpretations, which are considerably easier than using electric and Newton's laws to interpret what is going on. But before we get to what voltage is, let's deal with some language issues. So we have language issues. Analogy. Position by itself is meaningless. Whereas displacement is meaningful. Displacement is relative to a reference point and tells you how one moves. Is relative to a reference point and tells one how motion occurs. In a similar manner, electric potential is meaningless. Whereas potential difference which is defined as voltage, is meaningful. Potential represents an electrical height. In this case, it's really a vertical height or a vertical position in this electric space, whereas voltage represents an electric height difference and tells the direction of motion. As you already know, calling the parameter potential is a hideous misnomer because most students immediately think of potential energy. They are not the same thing. Once again, calling this parameter potential is a hideous misnomer because most immediately think of potential energy. They are not the same things. So when I teach Physics 4B, I mold my students to not call it potential, but think of it as a topographical parameter. So in other words, we don't start by using the word potential. We start that it's a topographical parameter, or a lot of the times I call it the landscape parameter. So that there is no connection between potential and potential energy. That being said, let's look at this here. So let's derive the potential field for parallel plates. So what do we know about parallel plates? If I have parallel plates, I imagine that we have plates that are relatively close to each other. And what we'll do here is that we'll say that this guy up here is a positive charged plate, and this guy is a negative charged plate down here at the bottom. Now, what we know here is that we have a field that's going to be constant. So our field for a parallel plate, we say that the electric field is a constant. So because it's constant then, if I place a charge in this field, that charge is then going to experience some electric force that pulls it down. And if our displacement is in this direction, we then do positive work. Okay, so here we go. So let's label these things. Let's say that this is our terminal point, which we'll call this point A, and we're going to call this point B, And what we'll do here is that we'll say that this is our lower plate, which we'll call that distance B, and this is our upper plate. So you can see here that we have a plate separation of delta R. So this is our plate separation. So here we go. So how do we deal with this mathematically? One calculates the potential field function by the work done by this electric field. So in other words here, we then say that the work, and because this is a conservative field, it has to be negative of the potential function, potential energy function, and this by definition is equal to minus Q delta V. So this right here tells us about how we define work and potential together for a conservative field, that is. So now if I look at the work done, so the work of the electric field is then going to be the integral from A to B, and it's going to be the force of the electric field dotted with the displacement, and then this will be QE, the integral from A equal to R to B equal to 0, and then I'm going to just have dr that I integrate. So as a result of this, we get Q times E times the quantity 0 minus R. In other words, what we're really getting is we're getting 0 minus Q E R. But this by definition has to be the negative of the electrical potential energy function, which is then related to the voltage or the potential difference. So if I choose the ground, so choosing the ground to be B equal to 0, then that tells me that the potential at B is 0. We now rewrite the potential function or the potential field as delta V is going to be VB minus VA, which will then be 0 minus BA, which in this case will be minus V of R, which is, of course, ER. Just writing it out because the charges are going to cancel out. So in other words, the potential field really looks as minus ER. Now, this is an important calculation. So why is this an important calculation? Charges that move in a potential field have, this is a little bit too close. Let me move this down just a little bit. have a different physical picture. And so if you look at the potential field picture, there's this electric field that we talked about earlier. This is our E field picture. And so if I have, then we see that our electric field is moving down like this, and this E field we know is a constant. And we know that this will be our high and this will be our low. So picture-wise, I actually see it this way. If I plot the potential function, you could see that our low here is going to be the ground, but it starts up at this height right here, and it goes down linearly. Why does it go down linearly? Because you could see that this is proportional to minus R. So when I look at this guy, this incline is the potential field, and this is what I call the topo, or the topographical, the landscape parameter. That is, if I was to now start to interpret this, so the physical potential picture is N, or is, in electrical, ramp slash incline, that tells charges how they will move. It's the ramp that tells us this. So if I convert this picture just a little bit, so how about converting this picture to include energy interpretations? Then I have this. I have a plate. And here's my plate right here. And then I have a second plate, which is right here. So when I look at that, this is my positive plate, this is my negative plate, and then this is what I'm going to call the ground, right? This, so when we start to interpret this of what's going on here, we then come in here and just say, this right here is the ground. We call this the ground because we are defining V equal to 0 here. And so this incline is the potential. So if you look at a charge, let's say I have a charge right here. And what this charge is going to do is that it's going to start at rest. And if I only have a single charge on an incline where there's no collisions whatsoever, then what we can do here is that we could now interpret this guy like this. This right here is the voltage. And that voltage represents the electrical height, right? So this guy right here is the electrical height change of charge. Furthermore, we use a digital multimeter measures this height. And that's what we mean by voltage. So if this starts off at rest, when it gets all the way down here to the bottom, it's now going to be moving at some speed that is not zero. So from an energy standpoint, the charge has initially this amount of electrical potential energy. And it has this amount of kinetic energy initially. By conservation of energy, mechanical energy, this has to be a constant. When you get all the way to the bottom, then that means that all of that kinetic energy has been transferred to all that potential energy is transferred to kinetic energy. And when it reaches the bottom, we know that that electrical potential energy is zero. It can't have more than that. So this being the case, we could now interpret what happens in a wire now. So using this model of voltage, let's interpret current in a copper wire. So the first thing that we'll do here is that we're going to look at that the voltage is equal to zero, or in other words, there is no E field in the wire. So if this occurs, only random thermal motion occurs with no net displacement. So the way I'll interpret this thing here is that I'm going to imagine here that I have a piece of copper wire. Let's say it looks like this. So if it looks like this, let's come in and let's imagine that this is the surface. And what we find here is that we're going to have copper ions distributed throughout this material here. So these guys here are the copper ions because one of the electrons is gone. And then I need a weakly bound electron. So this right here is the electron. So what happens to the electron? Well, if thermal motion occurs, then this is what's going to happen. There's going to be bounce, there's going to be something like this, and it comes back to its original spot. It's a flat surface. So what we're seeing here is that we have a flat surface with no height change and only random motion. So there's no net flow. Now what happens here is that now we're going to put a voltage across this. So now we have a voltage, which then tells me that the E field inside the wire has a small field here. So now what happens here? The copper wire is now inclined. So if I look at this thing, I now have a wire that's going to look something like this. Let's see how I can draw this. Let's see if I do it from here to here. So now this thing is inclined. I still have my copper ions here, but now when I put my electron in here, let me be careful first. So here, what you're seeing here is that now I have a height change. So what actually happens when I have a height change? The electron now has a superposition of two motions. So it is random. Oops, that's not what I wanted. It is random, but it's also this random is also colliding, but there is a drift in motion coming down. So in other words, I now have current flow occurring, and that's because there's an incline and it ramps it up.